66 million years ago, Earth entered a period of catastrophic disruption that would permanently alter the trajectory of life on this planet. The evidence of that disruption is preserved in rock, in chemistry, and in the fossil record. A global boundary layer of iridium-enriched clay that marks the precise moment when the Cretaceous period ended and the Paleogene began. For decades, the dominant explanation for that boundary rested on a single event: the collision of an asteroid roughly 12 kilometers in diameter with the shallow carbonate platform of what is now Mexico's Yucatan Peninsula. That impact, which produced the Chicxulub crater, a structure approximately 180 kilometers across, became the accepted mechanism behind one of the most severe mass extinctions in Earth's history. The scientific framework built around it was robust, internally consistent, and supported by converging lines of physical evidence gathered over more than 4 decades of research. But the geological record does not always yield its contents in a single reading. Some evidence remains buried, not metaphorically, but literally, beneath hundreds of meters of accumulated sediment on the floors of ocean basins that have not been systematically surveyed at high resolution. In 2022, a research team led by Justine Nicholson of Heriot-Watt University, analyzing seismic reflection data collected off the coast of West Africa, identified an anomalous subsurface structure on the Guinea Plateau, approximately 400 kilometers off the coast of Guinea, beneath roughly 300 to 400 meters of Paleogene sediment and around 900 meters of water. The feature's geometry was immediately striking: a near-circular faulted rim, approximately 8.5 kilometers in diameter, a central uplift, a surrounding depression, and a surrounding damage zone. Morphological characteristics consistent with a complex hypervelocity impact crater. The site was named the Nadir Crater, after the nearby Nadir seamount, located approximately 100 kilometers to the south. Before we go further, take a moment to consider where you're watching from, which country, and how distant it is from a time when Earth may have faced more than one cosmic impact, with evidence hidden beneath layers of rock and ocean floor for tens of millions of years. If these journeys through Earth's mysteries keep drawing you in, consider subscribing to continue exploring them. It's always fascinating to see how far these stories travel. Lower the lights, settle into stillness, and let the present fade as we trace faint clues through ancient sediments, searching for the forgotten mark of an event that almost vanished from history. The initial 2022 identification was based on 2-dimensional seismic reflection data, which established the structure's basic geometry and stratigraphic context with sufficient clarity to propose an impact origin. But it was the subsequent acquisition and analysis of high-resolution 3-dimensional seismic data that resolved the crater's internal anatomy in definitive detail. Published in 2024 in Communications Earth and Environment, the 3-dimensional survey revealed a structure of considerable complexity: a near-circular faulted rim, now refined to approximately 9.2 kilometers in diameter, surrounded by an outer brim approximately 23 kilometers across, defined by concentric normal faults, and an extended damage zone. Internally, the crater features a central uplift, rising approximately 350 meters from the crater floor, with spiral-shaped thrust faults indicating that the impactor struck at an oblique angle, entering from the northeast at approximately 20 to 40 degrees to the surface. This body of structural evidence confirmed the Nadir Crater's impact origin beyond reasonable doubt, formally establishing it as one of the few well-characterized marine impact structures identified in the geological record. The impactor responsible for the Nadir structure is estimated to have been approximately 400 to 500 meters in diameter, considerably smaller than the Chicxulub object, but still a body of substantial mass, traveling at a velocity of approximately 20 kilometers per second at the moment of contact. At that scale and speed, the energy released upon impact would have been equivalent to roughly 1,000 times the yield of the largest nuclear weapon ever detonated. The target was not continental crust, but an ocean basin approximately 800 to 900 meters deep, a condition that fundamentally shaped the physical sequence of the impact. Rather than excavating dry rock, the projectile passed through a water column before striking the seafloor, a configuration that altered the pressure dynamics, the distribution of ejecta, and the generation of secondary effects in ways that distinguish marine impacts from their continental counterparts. The three-dimensional seismic data allowed researchers to reconstruct the sequence of events that followed the collision with unusual precision. Within seconds of impact, the energy of the collision vaporized both the impactor and the surrounding sediment. The removal of crustal material triggered an immediate rebound, a vertical uplift of deeper substrate responding to the sudden release of lithostatic pressure, forming the central peak that remains visible in the seismic record today. Seawater was driven outward from the impact site by the expanding shockwave, generating a tsunami estimated at approximately 500 meters in height at the point of origin. In the minutes, hours, and days that followed, liquefied seawater surged repeatedly in and out of the partially evacuated crater, a process of tsunami resurgence that carved gullies into the crater's flanks and transported a mixture of sediment and impact glass, material known as suvite, back into the crater interior, where it accumulated as a distinct depositional layer now preserved in the subsurface record. What made the Nadir Crater's conformation scientifically significant extended beyond the discovery of a previously unknown impact structure. Its stratigraphic position placed its formation at or very near the Cretaceous-Paleogene boundary, within the same narrow temporal window approximately 66 million years ago as the Chicxulub impact event. At the resolution of the available geological data, the two events are effectively simultaneous. The probability of two independent asteroid impacts of significant magnitude occurring within the same geological instant by random chance alone is considered extremely low under conventional models of impact flux, which suggest that objects 400 meters or larger strike Earth at intervals on the order of hundreds of thousands to millions of years. This statistical tension led researchers to consider whether the two impactors may have been components of the same parent body, a fragmented asteroid or binary system that separated prior to Earth encounter and delivered multiple projectiles in rapid succession. The authors of the 2024 study acknowledged this possibility while also noting that an independent, coincidental impact cannot be excluded on current evidence alone. The confirmation of the Nadir Crater also highlighted how much of Earth's impact history remains effectively invisible to conventional survey methods. Of the approximately 200 confirmed impact structures currently catalogued on Earth's surface, the large majority are located on continental landmasses, where geological surveys are more extensive and surface exposures allow direct physical sampling. Oceanic impact craters are substantially underrepresented in the global catalogue, not because ocean impacts are intrinsically rare, given that water covers approximately 71% of Earth's surface, but because they are harder to detect, are subject to modification by seafloor spreading and sediment burial, and are frequently destroyed entirely by subduction over geological timescales. The Nadir Crater survived because the Atlantic crust on which it formed has remained intact and largely undisturbed since the Cretaceous period, allowing a 66-million-year-old structure to persist beneath its sediment cover until the resolution of modern three-dimensional seismic imaging made it visible. The age of the Nadir Crater remains constrained within an uncertainty of approximately 1 million years, a range precise enough to establish its temporal association with the Cretaceous-Paleogene boundary, but not yet narrow enough to determine whether the impact preceded, coincided with, or followed the Chicxulub event by any measurable interval. Reducing that uncertainty to a geologically meaningful resolution requires physical samples from the crater itself, sediment cores and rock material extracted from the structure that could be subjected to isotopic dating, geochemical analysis, and microscopic examination for the diagnostic signatures of impact metamorphism. A drilling proposal targeting the Nadir structure has been developed by the research team, with the objective of recovering cores from beneath 900 meters of water and 300 meters of overlying rock. Those samples, once obtained, would allow researchers to determine the crater's precise age and to characterize the physical and environmental consequences of the impact with a level of detail that remote sensing data alone cannot provide. The Nadir Crater, defined by the outline of its buried rim beneath the Atlantic floor, represents a geological event that occurred at one of the most consequential moments in the history of life on Earth. By the final million years of the Cretaceous period, life on Earth had reached a state of extraordinary ecological complexity. The planet was warmer than it is today, by an estimated 4 to 8 degrees Celsius on average, with no permanent polar ice caps and sea levels running approximately 100 meters higher than their current position. Continental configurations were recognizably modern in broad outline, but meaningfully different in detail. North America was divided along its interior by the Western Interior Seaway, a shallow epicontinental sea stretching from the Arctic Ocean to the Gulf of Mexico, effectively splitting the landmass into two separate continental platforms. Europe was an archipelago of large islands. India was an isolated subcontinent, drifting northward across the Tethys Ocean. The arrangement of land and water shaped atmospheric circulation, ocean currents, and the distribution of ecosystems in ways that produced a global biosphere fundamentally unlike anything that exists today. The terrestrial ecosystems of the late Cretaceous were dominated, as they had been for more than 150 million years, by non-avian dinosaurs. But the dinosaur faunas of the final Cretaceous stage, the Maastrichtian, which lasted from approximately 72 to 66 million years ago, were not a single uniform community spread across the globe. They were regionally differentiated assemblages, shaped by the geography of the continents and the ecological conditions of specific environments, and they varied considerably in composition from one landmass to another. In Western North America, where the fossil record of the latest Cretaceous is exceptionally well preserved, the fauna was dominated by large-bodied herbivores and the apex predators that hunted them. Ceratopsians, horned and frilled dinosaurs, such as Triceratops and related genera, moved in groups across coastal floodplains and forested lowlands, processing tough, fibrous vegetation with their shearing dental batteries. Hadrosaurs, the duck-billed dinosaurs, were among the most ecologically successful herbivores the planet had ever produced, with some species reaching body lengths exceeding 10 meters and forming aggregations that would have numbered in the hundreds or thousands of individuals during seasonal migrations. Above these herbivore populations, in terms of trophic position, stood the large theropod predators. Tyrannosaurus rex, the largest terrestrial predator of its time and one of the largest that has ever existed, reached body masses estimated between 8,000 and 14,000 kilograms and lengths of up to 12 to 13 meters. It occupied the apex of the food chain in its ecosystem with a combination of physical power, sensory acuity, and behavioral sophistication that current evidence suggests was considerably more complex than earlier reconstructions indicated. Bite force measurements derived from skull geometry indicate that Tyrannosaurus was capable of generating forces exceeding 35,000 to 57,000 newtons, sufficient to crush bone, and isotopic analysis of its remains suggests it occupied a dietary niche that included both active predation and opportunistic scavenging. These were not primitive or declining animals at the close of the Cretaceous. The evidence indicates they were ecologically successful, well-adapted, and thoroughly integrated into functional ecosystems that had been operating continuously for tens of millions of years. Alongside the large ceratopsians and hadrosaurs, the late Cretaceous terrestrial environment supported a diverse array of smaller and medium-sized dinosaurs. Ankylosaurs, heavily armored, low-slung herbivores with masses reaching several tons, foraged across the same floodplains. Pachycephalosaurs, with their thickened, domed skulls, occupied niches that likely involved both herbivory and intraspecific competition. Smaller theropods, including dromaeosaurids and troodontids, hunted prey ranging from insects and small vertebrates to juvenile dinosaurs, filling ecological roles analogous to those occupied today by mid-sized mammalian carnivores. And within this theropod diversity, one lineage had already made a transition that would prove to be of enormous long-term significance. The avian dinosaurs, birds, had been present since the Jurassic period, and by the Maastrichtian had diversified into a range of ecological forms, some of which would survive what was approaching. The vegetation underpinning these terrestrial ecosystems had itself undergone a profound transformation during the Cretaceous. Flowering plants, angiosperms, had diversified explosively during the Middle Cretaceous, and by the Maastrichtian had become the dominant form of vegetation across most of the planet's terrestrial surface. Forests of broad-leaved deciduous and evergreen trees covered extensive areas of the continental interiors and coastal lowlands. Ferns and cycads persisted as components of the ground cover and understory. The spread of angiosperms had driven corresponding diversifications in the insects that depended on them for food and reproduced in partnership with them through pollination. And those insect diversifications, in turn, supported the food webs of small vertebrates, including the early mammals that moved through the leaf litter and underbrush of Cretaceous forests in the shadows of the dominant dinosaur fauna. Those mammals were not the large, ecologically prominent forms that would come to define the Cenozoic era. The mammals of the late Cretaceous were predominantly small-bodied, most weighing less than a kilogram, and largely nocturnal or crepuscular in habit, a behavioral pattern that current hypotheses suggest developed as an adaptation to avoid predation by dinosaurs active during daylight hours. They occupied niches as insectivores, omnivores, and seed-eaters, living within the structural complexity of forest environments, where their small size and generalized diets allowed them to exploit resources unavailable to larger animals. Their ecological significance at the close of the Cretaceous was modest in absolute terms. Nothing in the structure of the late Cretaceous biosphere would have suggested that these small, largely unremarkable animals were positioned to inherit the terrestrial world. The marine environments of the late Cretaceous were no less complex than the terrestrial ones. The western interior seaway of North America, along with the shallow epicontinental seas that covered portions of Europe and other landmasses, supported ecosystems of extraordinary productivity. Mosasaurs, large, secondarily aquatic squamates that had evolved from terrestrial lizard ancestors, had diversified into a range of body plans and feeding strategies, with the largest species reaching lengths exceeding 13 to 17 meters, and occupying the apex predator role in marine food chains. Plesiosaurs, the long-necked marine reptiles that had been a feature of ocean ecosystems since the Triassic, persisted into the latest Cretaceous in reduced but still ecologically significant numbers. Ammonites, coiled cephalopod mollusks with external shells, were ubiquitous in Cretaceous seas, with hundreds of species distributed across ocean basins worldwide, forming a critical component of mid-level marine food webs as both predators of smaller invertebrates and prey for larger marine vertebrates. The open ocean supported large predatory fish, including members of the genus Xiphactinus, which reached body lengths of up to 6 meters and were among the dominant piscivores of the late Cretaceous seas. Sharks were present in considerable diversity, though the enormous forms that would characterize later Cenozoic oceans had not yet appeared. Sea turtles navigated open water. Marine birds, Hesperornithines, flightless diving birds with teeth, pursued fish through shallow coastal waters. The productivity of these marine ecosystems was ultimately grounded in the photosynthetic activity of phytoplankton in the upper ocean, which supported zooplankton communities, which in turn supported progressively larger consumers in a food web of considerable structural depth and biological diversity. On the day, or more precisely, within the interval of time that the geological record cannot resolve, below the scale of approximately 10,000 years, before the impact events that would terminate the Cretaceous, none of these ecosystems showed signs of imminent collapse. The evidence preserved in the fossil record and in the geochemical signatures of latest Cretaceous sediments does not support the hypothesis, advanced in some earlier frameworks, that dinosaur diversity was already in significant decline in the final millions of years of the Maastrichtian. More recent analyses of the fossil record, accounting for the uneven sampling of geological formations, indicate that large-bodied dinosaur faunas in North America maintained relatively stable diversity up to the level of the Cretaceous-Paleogene boundary. The ecosystems of the late Cretaceous were not systems under stress, moving toward an internally generated collapse. They were functioning, diverse, and productive biological communities operating within a set of environmental conditions that had prevailed, with gradual variation across geological timescales. There were, however, background stresses operating on geological timescales that the organisms of the late Cretaceous were entirely unequipped to perceive or respond to. The Deccan Traps, a massive volcanic province in what is now west-central India, had been erupting episodically since approximately 66.5 million years ago, releasing large volumes of sulfur dioxide, carbon dioxide, and other gases into the atmosphere. The environmental effects of this volcanism, including episodes of atmospheric cooling from sulfate aerosols, followed by longer-term warming from elevated carbon dioxide concentrations, may have introduced instability into global climate and ocean chemistry during the final 500,000 years of the Cretaceous. The magnitude of these effects relative to the subsequent impact events remains an active area of scientific investigation, but current evidence indicates that Deccan volcanism alone was insufficient to drive a mass extinction of the scale that ultimately occurred. It may, however, have left ecosystems operating under conditions of mild but measurable environmental stress when the impacts arrived. Sea level was also changing during the late Maastrichtian. Regression, the gradual withdrawal of shallow epicontinental seas from continental interiors, had been reducing the extent of the warm, shallow marine environments that supported high-productivity coastal ecosystems. The Western Interior Seaway, which at its maximum extent had been more than 1,000 kilometers wide, had contracted substantially by the end of the Cretaceous as sea levels fell. These changes in marine geography affected the distribution of species and the connectivity of populations, but they did not constitute an extinction-level perturbation. They were the ordinary fluctuations of a dynamic planet, within the range of variation that life had navigated repeatedly across the preceding hundreds of millions of years. The atmosphere that surrounded the late Cretaceous Earth was oxygen-rich and carbon dioxide elevated relative to modern conditions, supporting the high metabolic demands of large-bodied ectothermic and endothermic animals alike. The carbon cycle, the sulfur cycle, the phosphorus cycle, all of the biogeochemical systems that regulate the habitability of Earth's surface were operating within bounds that had been established over billions of years of planetary evolution, and that the biosphere had continuously shaped through its own metabolic activity. The planet was, in every measurable respect, a functioning biological system of global extent, with billions of individual organisms distributed across its surface and through its oceans, all participating in the continuous exchange of energy and matter that constitutes the living world. Into this system, without warning, without precursor, and without any mechanism by which the organisms of the late Cretaceous could have detected what was approaching, 2 points of light were already descending through the inner solar system, their trajectories converging on the surface of the Earth. The ecosystems of the Maastrichtian, refined across tens of millions of years of evolutionary history, were entirely unprepared for what was seconds or hours or days away. The geological record preserves the evidence of what existed immediately before that moment, in bone, in pollen, in the chemistry of carbonate shells accumulated on the seafloor, with a fidelity sufficient to reconstruct the world that was about to end. The object that would form the Nadir Crater entered Earth's atmosphere over the South Atlantic region, traveling at approximately 20 kilometers per second, a velocity that, by the standards of hypervelocity impact mechanics, falls within the typical range for asteroidal impactors, but represents a speed at which ordinary physical intuitions about matter and energy cease to apply. At 20 kilometers per second, an object covers a distance equal to the width of a large city in less than 1 second. The atmosphere, which to a slower-moving body would represent a significant barrier, offered effectively no meaningful deceleration to an object 400 to 500 meters in diameter traveling at this velocity. The transit from the upper atmosphere to the ocean surface would have taken approximately 10 seconds. During those 10 seconds, the interaction between the impactor and the atmosphere generated effects visible across a vast region. The compression of air ahead of the descending object produced a plasma channel of superheated gas extending from the upper atmosphere to the surface. A column of ionized air radiating energy across the electromagnetic spectrum, including intense ultraviolet and visible light. The luminosity of this event would have been visible in daylight across much of the Atlantic basin and adjacent continental regions. To any organism within line of sight, the descending object would have appeared as an intensifying point of light, growing rapidly in apparent size over a period of seconds, reaching a brightness exceeding that of the sun before the moment of impact. The acoustic signature, a deep, resonant pressure wave propagating through the atmosphere, would have followed the light by minutes, depending on distance, arriving as a sound unlike anything produced by ordinary geological or meteorological processes. The impactor struck ocean water approximately 800 to 900 meters deep. The physical sequence that followed unfolded across timescales ranging from microseconds to hours, with each phase governed by a distinct set of physical processes and producing consequences of a different character and spatial extent. In the first microseconds of contact, the kinetic energy of the impactor, equivalent in total to many thousands of megatons of high explosive, began transferring into the water column and the underlying seafloor at a rate that generated pressures measured in millions of atmospheres at the contact interface. Under these conditions, the distinction between solid, liquid, and gas becomes physically meaningless. Both the impactor and the rock and sediment of the seafloor at the point of contact were converted into a superheated plasma within a fraction of a second. The impactor ceased to exist as a discrete object, essentially instantaneously upon contact. The expanding sphere of vaporized and superheated material drove a shockwave outward through the surrounding ocean water and downward into the oceanic crust at velocities far exceeding the speed of sound in those media. Through water, the shockwave propagated at several kilometers per second, compressing and accelerating the water column ahead of it and leaving a zone of cavitation and turbulent flow in its wake. Through the basaltic oceanic crust beneath the impact site, the shockwave induced pressures sufficient to produce shock metamorphism in the mineral grains of the rock, generating planar deformation features in quartz and other minerals, converting some material into high-pressure polymorphs, and in the immediate vicinity of the impact point, melting rock that would later solidify as impact glass distributed across the crater interior and its surrounding ejector field. The crater itself formed within seconds. The initial contact excavated a transient cavity in the seafloor, a bowl-shaped depression driven downward and outward by the expanding shockwave, reaching a depth and diameter far exceeding the final dimensions of the preserved structure. This transient cavity was inherently unstable. Within seconds of its maximum excavation, the walls of the cavity began to collapse inward under the influence of gravity, and the floor of the cavity rebounded upward as the lithostatic pressure removed by excavation was released. This rebound formed the central uplift, the 350-meter peak visible today in the three-dimensional seismic data, while the collapsing walls produced the terraced interior structure and the system of concentric normal faults that extend outward from the rim across the surrounding seafloor. The spiral geometry of thrust faults identified in the seismic data records the oblique angle of the impact trajectory, preserving, in the permanent deformation of the rock, a directional signature of the impactor's approach from the northeast. The water column above the impact site behaved in a manner distinct from the solid rock below it. The initial shockwave drove the ocean outward from the impact point, effectively excavating a temporary cavity in the water itself, a column of open space extending from the seafloor to the surface, surrounded by a rapidly expanding wall of displaced seawater. As this water column collapsed back into the cavity, and the steam generated by the vaporization of seawater condensed and recondensed at the margins of the impact zone, the convergence of water from all directions produced an enormous central jet, a column of water and steam driven upward through the surface and into the lower atmosphere, carrying with it vaporized and fragmented material from both the impactor and the seafloor. This material, once lofted into the atmosphere, began a process of dispersal that would carry the chemical and physical signatures of the impact far beyond the immediate impact site. The tsunami generated by the impact was a consequence of the rapid displacement of the water column rather than of seafloor deformation in the manner of earthquake-generated tsunamis. Numerical simulations constrained by the crater's geometry and the estimated impactor parameters indicate that the initial wave height at the point of generation was approximately 500 meters, a figure that represents not a surface wave in the conventional sense, but a complex, three-dimensional disturbance in the water column propagating outward from the impact point at velocities determined by the depth of the ocean. In deep water, tsunami propagation velocities approach 700 to 800 kilometers per hour. The initial wave would have reached the coastlines of West Africa and South America within hours of impact, arriving not as a single wave, but as a train of waves with the leading edge carrying the greatest energy, capable of inundating coastal environments to depths and distances determined by local bathymetry and coastal topography. The energy partitioned into the tsunami represented only a fraction of the total impact energy. The remainder was distributed across shockwave propagation through rock, thermal radiation, atmospheric blast, and the lofting of ejecta. The atmospheric shockwave, a pressure pulse propagating outward from the impact point through the air, would have caused direct physical damage to vegetation and structures across a radius of hundreds of kilometers, with wind velocities in the immediate vicinity of the impact exceeding those of any meteorological storm system. Further from the impact site, the overpressure diminished progressively but remained detectable, in physical terms, across much of the Atlantic basin. The ejecta plume, the column of vaporized, melted, and fragmented material driven into the atmosphere by the energy of the impact, carried material to altitudes reaching the stratosphere. Coarser ejecta, including centimeter-scale and millimeter-scale particles of shocked rock and impact glass, followed ballistic trajectories that would bring them back to the surface within minutes to hours across a region extending thousands of kilometers from the impact site. Finer material, micrometer-scale particles of silicate dust and sulfate aerosols, derived from the vaporization of sulfur-bearing seafloor sediments, reached the upper atmosphere and began dispersing on timescales of days to weeks, carried by stratospheric wind patterns across the globe. This fine material, once globally distributed, would begin intercepting incoming solar radiation and reducing the energy reaching the surface, a process with consequences that would extend far beyond the immediate physical effects of the impact itself. At the impact site, within the first hours following the collision, the crater was undergoing a process of hydraulic resurgence. Seawater, surging back into the partially evacuated basin, carried with it a mixture of suspended sediment, fragmented rock, and impact-generated glass. This material settled into the crater interior in a series of depositional pulses driven by the oscillating inflow and outflow of water associated with the tsunami resurgence. A repeated sloshing of the water column that carved the gullies now visible on the crater's flanks in the seismic data and deposited the suvite layer that now forms a distinctive stratigraphic marker within the crater's sediment fill. Within days, the gross morphology of the crater was established in its permanent form, buried progressively over the following 66 million years beneath the accumulating sediment of the Atlantic floor, until the resolution of three-dimensional seismic imaging brought it back into view. The ocean that received the Nadir impactor was not a passive medium. It was a dynamic, three-dimensional system, layered by temperature and salinity, structured by circulation patterns, driven by wind and density gradients, and populated from surface to seafloor by communities of organisms whose ecological relationships had been developing continuously across hundreds of millions of years. When the impactor struck, that system did not simply absorb the energy of the collision and return to equilibrium. It was transformed, violently and on multiple spatial scales simultaneously, in ways that propagated outward from the impact site across the full width of the Atlantic basin and beyond. The immediate physical consequence of the impact on the surrounding ocean was the generation of a displacement wave of extraordinary initial amplitude. Current models derived from the crater's confirmed dimensions and estimated impactor parameters place the wave height at the point of origin at approximately 500 meters. This figure, requires context to be understood correctly. The largest tsunami waves produced by major subduction zone earthquakes, events releasing energy on the order of magnitude of the 2004 Indian Ocean earthquake, itself one of the most energetic seismic events recorded in the modern era, generate initial wave heights measured in tens of meters under typical conditions. The displacement produced by the Nadir impact exceeded those values by more than an order of magnitude at the source. The wave that radiated outward from the Guinea Plateau was not a tsunami in the sense familiar from geological or historical records. It was a fundamentally different category of oceanic disturbance, operating at a scale without modern analog. As the wave propagated outward from the impact site through the deep Atlantic, its behavior was governed by the physics of water wave propagation in the open ocean. In water depths of several kilometers, long-period waves travel at velocities proportional to the square root of water depth multiplied by gravitational acceleration, a relationship that produces propagation speeds in the range of 700 to 800 kilometers per hour for waves crossing the deep ocean floor. At these speeds, the wavefront would have reached the continental shelf of West Africa within approximately 30 to 60 minutes of impact, and the coastline of South America within 2 to 3 hours. The Mid-Atlantic Ridge, a submarine mountain chain running roughly north to south through the center of the Atlantic Basin, would have partially reflected and refracted the wave energy, producing complex interference patterns in the propagating wave field that concentrated energy in some directions and reduced it in others. The transformation of the wave as it encountered the shallow water of continental shelves was where its destructive potential was most fully realized. The process of shoaling, the deceleration and vertical amplification of a wave as it moves from deep to shallow water, compressed the wave's horizontal extent while increasing its height. A wave that had propagated across thousands of kilometers of open ocean at relatively low amplitude relative to ocean depth arrived at coastal margins as a wall of water whose height depended on local bathymetric conditions, but would in many locations have reached tens to hundreds of meters above normal sea level. The coastlines of West Africa and, across the Atlantic, the eastern margins of South America would have experienced inundation on a scale that restructured the physical geography of coastal environments and destroyed the biological communities inhabiting them. Coastal forests, river delta ecosystems, and the shallow marine communities of continental shelves were exposed to wave energies far exceeding anything produced by ordinary geological processes operating at those locations across millions of years. The effects on the marine ecosystem were not limited to the mechanical destruction caused by wave action. The impact had also introduced an enormous quantity of heat, fragmented material, and chemically altered seawater into the upper ocean across the affected region. The vaporization of seawater at the impact site and the subsequent condensation and fallback of water vapor and entrained material altered the temperature and chemistry of the surface ocean across a region extending hundreds of kilometers from the crater. The thermal pulse associated with the impact, heat transferred from the superheated plasma of the initial collision into the surrounding water, would have elevated ocean surface temperatures in the immediate vicinity of the impact to levels lethal to any marine organism unable to escape the affected zone rapidly. Beneath the surface, the shockwave that had propagated through the ocean floor and underlying crust triggered a secondary consequence of considerable geological significance. The sediment layers of the Guinea Plateau and the surrounding Atlantic seafloor, accumulated over millions of years of slow pelagic deposition, were subjected to accelerations far exceeding their mechanical stability thresholds. Submarine landslides, the sudden downslope failure of large volumes of accumulated sediment, would have been triggered across the continental margins surrounding the impact site. These slides, mobilizing material across areas potentially extending hundreds of kilometers from the impact point, would themselves have generated secondary tsunami waves, added to the suspended sediment load of the deep ocean, and disrupted the benthic ecosystems of the seafloor across vast areas through burial, erosion, and the abrupt alteration of substrate conditions. The deep ocean floor, normally one of the most physically stable environments on Earth, characterized by near-freezing temperatures, complete darkness, and sedimentation rates measured in millimeters per 1,000 years, was exposed to conditions of extraordinary physical violence. Turbidity currents generated by the mobilization of seafloor sediment flowed outward from the impact site and from the triggered landslide zones along the seafloor at velocities that could erode and transport material across distances of hundreds to thousands of kilometers. The benthic fauna of the affected seafloor, communities of invertebrates, microbial mats, and deep-sea fish adapted to the extreme stability of the abyssal environment, were exposed to burial, erosion, and the physical destruction of their habitat on timescales of hours to days. Recovery of these communities, even in the absence of any other perturbation, would have required decades to centuries. In the upper ocean, the biological consequences of the impact manifested through a different set of mechanisms. The phytoplankton communities responsible for the majority of oceanic primary production, the foundation of marine food webs, are sensitive to changes in light availability, nutrient concentrations, and physical mixing of the water column. The impact introduced all three of these variables simultaneously and abruptly. The thermal and mechanical disturbance of the upper ocean disrupted the stable stratification that, in tropical and subtropical regions, separates nutrient-poor surface waters from nutrient-rich deep water. This disruption would initially have introduced elevated nutrient concentrations into the surface layer, potentially stimulating short-term algal growth in localized regions around the impact site. But the same physical mixing that redistributed nutrients also introduced deep, cold water into the surface layer, reducing sea surface temperatures in affected areas and altering the physical conditions under which phytoplankton communities could maintain their productivity. The ammonites that populated the late Cretaceous Atlantic in extraordinary diversity were particularly vulnerable to disruption of surface ocean conditions. These externally shelled cephalopods spent the early stages of their life cycles in the upper water column, where their eggs and juveniles were subject to the temperature, chemistry, and productivity conditions of the surface ocean. A sustained disturbance to those conditions, through thermal disruption, altered chemistry, or reduced primary productivity, would have interrupted the reproductive cycle of ammonite populations across affected ocean regions, a vulnerability that would prove consequential as the environmental effects of the impact extended beyond the immediate physical disturbance and began operating on regional and ultimately global scales. The seafloor beneath the impact site was permanently altered by the collision. The crater itself, 9.2 kilometers in rim diameter, with a central uplift of 350 meters and a surrounding damage zone extending to approximately 23 kilometers, represented a reorganization of seafloor topography that redirected local bottom currents, altered sediment transport pathways, and created a new set of physical habitats on and around the crater structure. In the immediate aftermath of the impact, the crater interior was filling with a mixture of impact melt, fragmented rock, and sediment transported by the repeated surge and withdrawal of seawater, a chaotic depositional environment that would eventually stabilize into the layered sediment fill now visible in the seismic record. The surrounding seafloor bore the imprint of the impact in the form of ejecta deposits, erosional surfaces created by the passage of the impact wave, and the deformation structures produced by the propagating shockwave through the oceanic crust. The Atlantic Ocean, 66 million years ago, was a younger and narrower basin than it is today, the product of roughly 100 million years of seafloor spreading since the initial breakup of the supercontinent Pangaea. Its restricted geometry relative to the modern ocean meant that the energy of the impact wave was contained within a basin with limited outlets, amplifying the repeated reflection and interference of wave energy off continental margins and mid-ocean ridges, and prolonging the duration of oceanic disturbance beyond what would be expected in a wider basin. The ocean that had, moments before the impact, been a functioning biological system of global ecological importance, had been converted, within hours, into a medium carrying the physical record of a catastrophic energy release, a record now preserved beneath 300 meters of sediment, in the geometry of a crater on the floor of the Atlantic. The Chicxulub crater, located beneath the northern Yucatan Peninsula and the adjacent Gulf of Mexico, measures approximately 180 kilometers in diameter, one of the largest confirmed impact structures on Earth, and the product of a collision releasing energy estimated at approximately 100 million megatons. The impactor responsible was roughly 12 kilometers in diameter, struck at a velocity of around 20 kilometers per second, and hit a target of shallow carbonate and evaporite rock, whose vaporization released enormous quantities of sulfur dioxide and carbon dioxide into the atmosphere. The physical and environmental consequences of that single event were sufficient, by themselves, to terminate the Cretaceous period and drive the extinction of approximately 75% of all species then living on Earth. The scientific case for Chicxulub as the primary driver of the end Cretaceous mass extinction is supported by decades of converging evidence: geochemical, stratigraphic, paleontological, and physical, and is not in serious scientific dispute. The confirmation of the Nadir Crater as a second impact structure of late Cretaceous age introduced a question that the existing framework for the extinction event had not been required to address. What does it mean for Earth to have been struck twice, at effectively the same geological moment, by objects whose arrival cannot be explained as coincidence under standard models of asteroid impact frequency? The statistical foundation of that question rests on well-established impact flux models, derived from crater counting on the Moon and other planetary bodies, combined with astronomical surveys of near-Earth object populations. These models indicate that asteroids 400 meters or larger in diameter, the minimum estimated size of the Nadir impactor, strike Earth at average intervals on the order of 100,000 years or more. Asteroids in the size range of the Chicxulub impactor, 10 kilometers or larger, strike at intervals estimated at 100 million years or more. The probability of two independent objects in these size ranges arriving at Earth within the same geological instant, a window that, at the resolution of current dating methods for the Nadir Crater, spans approximately 1 million years, is extremely low but not precisely quantifiable without narrower age constraints on the Nadir event. If future drilling and isotopic dating of crater material reduces that uncertainty window significantly, and if the two impacts are confirmed to have occurred within thousands rather than hundreds of thousands of years of each other, the statistical case for a physical connection between them becomes substantially stronger. The most frequently discussed mechanism for a physical connection is the fragmentation of a parent body prior to Earth encounter. Asteroids in the inner solar system are not uniformly solid, monolithic structures. Many are loosely consolidated aggregates, sometimes described as rubble piles, held together by gravitational attraction rather than structural cohesion. When such a body passes within the Roche limit of a large gravitational body, tidal forces can overcome the internal cohesion of the aggregate, and cause it to separate into multiple fragments. A close encounter with the Earth-Moon system, or with another planetary body earlier in the object's orbital history, could have produced a cluster of fragments traveling on closely related trajectories. If the Chicxulub impactor and the Nadir impactor were both fragments of a single parent body that underwent tidal disruption prior to Earth encounter, their near-simultaneous arrival at Earth becomes a physically natural consequence of that fragmentation rather than a statistical anomaly. A parallel scenario involves binary asteroid systems, pairs of gravitationally bound objects orbiting a common center of mass, which are more common in the near-Earth asteroid population than early surveys indicated. Observations and modeling of near-Earth asteroid populations suggest that approximately 15% of asteroids larger than 200 meters in diameter are binary or multiple systems. If the Chicxulub and Nadir impactors were components of a binary system, they would have traveled through space on closely coupled trajectories and encountered Earth's gravitational field essentially simultaneously. The separation distance between the two impact sites, with Chicxulub located in what is now the Gulf of Mexico and Nadir located off the coast of West Africa, is consistent with a binary system whose components separated upon gravitational interaction with Earth and struck different parts of the planet's surface within a short interval of time. Neither the fragmentation nor the binary hypothesis can be confirmed or excluded on the basis of currently available evidence. The age uncertainty of the Nadir Crater, currently constrained to within approximately 1 million years of the Cretaceous-Paleogene boundary, does not yet permit the kind of temporal resolution needed to determine whether the two impacts were separated by centuries, millennia, or hundreds of thousands of years. At geological resolution, all of these intervals are effectively simultaneous, but their physical and environmental implications are very different. Two impacts separated by centuries would have produced overlapping and compounding environmental effects, a single prolonged catastrophe rather than two discrete events. Two impacts separated by hundreds of thousands of years would have been environmentally independent, with the biosphere potentially recovering partially from one before the second arrived. What current evidence does establish is that the Nadir impact, taken independently of Chicxulub, would have been a regionally catastrophic event. An impactor 400 to 500 meters in diameter, striking a deep ocean basin, releases energy sufficient to generate a 500-meter tsunami, trigger submarine landslides across adjacent continental margins, loft stratospheric ejecta, and produce regional-scale atmospheric disturbance. In the context of an otherwise stable biosphere, such an event would register clearly in the geological record and would likely drive significant regional extinctions. In the context of a biosphere already absorbing the global consequences of the Chicxulub impact, the additional energy input and environmental disruption represented by the Nadir event, regardless of its precise timing relative to Chicxulub, would have compounded an already catastrophic situation. The difference in scale between the two impactors is significant, but does not translate directly into a proportional difference in environmental consequence. The Chicxulub impactor, roughly 12 kilometers in diameter, released energy approximately 1,000 times greater than the estimated Nadir impactor. But the relationship between impactor energy and environmental damage is not linear across all categories of effect. The injection of material into the stratosphere, the generation of acid rain through the atmospheric oxidation of impact vaporized sulfur and nitrogen compounds, and the disruption of ocean chemistry through ejecta fallout all scale with impactor energy in ways that mean a second impact, even substantially smaller than the first, adds meaningfully to the total environmental burden imposed on the biosphere. The cumulative effect of two impacts, separated by any interval short enough that the biosphere had not recovered from the first, would exceed the sum of their individual effects. The physical record of both impacts is preserved in the geological boundary layer that marks the end of the Cretaceous. The iridium anomaly, the globally distributed enrichment of the platinum group element iridium in the thin clay layer at the Cretaceous-Paleogene boundary, is the geochemical signature of extraterrestrial material dispersed globally from the Chicxulub impact. Whether the Nadir impact contributed a detectable additional signal to that layer, or whether its contribution is inseparable from the Chicxulub signal at current analytical resolution, remains an open question. Targeted geochemical analysis of boundary layer material from locations in the Atlantic Basin, where proximity to the Nadir impact site might have produced a locally elevated signal, could potentially distinguish between contributions from the two events, provided that the analytical resolution is sufficient to detect the smaller impactor's geochemical footprint against the background of the much larger Chicxulub signal. The existence of two confirmed impact structures at the Cretaceous-Paleogene boundary raises a further question that current evidence cannot resolve. Were there additional impacts that have not yet been identified? The incompleteness of the oceanic impact crater record, a consequence of the technical difficulty of deep ocean surveying, the destruction of oceanic crust by subduction, and the burial of structures beneath accumulated sediment, means that the confirmed crater count for any given time interval represents a minimum rather than a complete census. If the Chicxulub and Nadir impactors were fragments of a larger disrupted body, the original parent object may have produced more than two significant fragments on trajectories intersecting Earth. Identifying additional impact structures of equivalent age, whether on ocean floors or on continental surfaces where erosion may have obscured their morphology, requires the kind of systematic, high-resolution surveying that has not yet been applied uniformly across Earth's surface. The Nadir Crater was discovered within a dataset collected for unrelated purposes. It is not possible, on current evidence, to determine how many similar structures remain undetected. The oceans of the late Cretaceous were, by any measure applicable to the history of marine life, among the most biologically productive and ecologically complex that Earth had yet produced. The long evolutionary history of marine vertebrates, stretching back across hundreds of millions of years, through fish, through the first tetrapods, through the secondary return of multiple tetrapod lineages to aquatic existence, had by the Maastrichtian generated a marine fauna of extraordinary diversity, occupying ecological roles from the sunlit surface waters to the deep benthic zone, and operating within food webs of considerable structural depth. At the apex of those food webs were the mosasaurs. These were not fish, and they were not dinosaurs. They were squamates, members of the same broad reptilian lineage that includes modern lizards and snakes, whose ancestors had returned to the ocean sometime in the mid-Cretaceous and diversified with remarkable speed into a range of body plans and feeding strategies. By the Maastrichtian, mosasaurs had become the dominant large predators of the open ocean worldwide, filling the ecological role that would later be occupied, in a different ocean, by large sharks and toothed whales. The largest mosasaur species, including Mosasaurus itself and the robust skulled Tylosaurus, reached body lengths of 13 to 17 meters and masses estimated in the range of several tons. Their dentition varied by genus. Some bore conical, piercing teeth suited to capturing fish and cephalopods. Others, broad, crushing teeth adapted for processing hard-shelled prey, including ammonites and marine turtles. Mosasaur remains have been recovered from late Cretaceous marine deposits on every continent, including Antarctica, indicating a global distribution made possible by their capacity for open ocean navigation and their physiological tolerance of a wide range of marine conditions. Below the mosasaurs in the trophic hierarchy, but no less significant in terms of ecological function, were the large predatory fish that patrolled the same ocean systems. Xephactinus, a large teleost fish reaching body lengths of up to 6 meters, was among the most widespread marine predators of the late Cretaceous. Fossil specimens of Xephactinus have been recovered, with the remains of smaller fish preserved within their abdominal cavities, direct physical evidence of predation events frozen in the geological record. These animals occupied a mid-level apex position in the marine food web, preying on smaller fish and themselves serving as prey for mosasaurs. Sharks were present in considerable diversity, though the dominant late Cretaceous shark fauna differed substantially from modern assemblages. Cretoxyrhina, sometimes called the Ginsu shark, reached lengths of approximately 6 to 7 meters and bore serrated teeth adapted for cutting through the flesh and bone of large prey, including mosasaurs and plesiosaurs, a feeding ecology documented by tooth marks preserved on the bones of these animals in the fossil record. The plesiosaurs, whose evolutionary history extended back to the Triassic period, persisted into the latest Cretaceous in 2 principal body plan variants. The long-necked plesiosaurs, plesiosauroids, bore small heads on extremely elongated necks, a configuration suited to capturing fish, and small cephalopods with rapid, targeted strikes. The short-necked, large-headed forms, pleosauroids, had declined substantially in diversity by the Maastrichtian relative to their earlier Mesozoic prominence. But isolated large-bodied representatives persisted in some ocean regions. Both groups were fully adapted to marine existence, unable to return to land, giving birth to live young in open water, as evidenced by fossil specimens preserving embryonic material within adult individuals. The ammonites represented the most diverse and numerically abundant component of the large-bodied invertebrate fauna in late Cretaceous seas. With hundreds of species distributed across ocean basins worldwide, these externally shelled cephalopods occupied a critical position in mid-level marine food webs. Their shells, coiled, chambered structures of calcium carbonate, ranging in diameter from a few centimeters to, in the case of the largest species, such as Parapuzosia sepenrodensis, nearly 2.5 meters, are among the most common macrofossils recovered from Cretaceous marine deposits, preserved in sufficient abundance to serve as primary stratigraphic index fossils for correlating rock layers across continents. The ammonites fed on zooplankton, small fish, and other invertebrates using a beak-like jaw structure, and were in turn preyed upon by mosasaurs, large fish, and marine reptiles. Their role as a link between planktonic food web components and larger predators made them a structural element of the marine ecosystem, whose loss would propagate through the food web in both directions. Alongside the ammonites, the late Cretaceous oceans supported large populations of inoceramid bivalves, giant clams reaching sizes of up to 1 meter in some species, rudist bivalves that formed reef-like structures in tropical shallow water environments, and echinoids, foraminifera, and calcareous nanoplankton that formed the biological foundation of carbonate sediment production on the ocean floor. The calcareous nanoplankton, single-celled photosynthetic organisms producing microscopic calcite plates called coccoliths, were quantitatively among the most important primary producers in the late Cretaceous ocean, and the slow rain of their shells onto the seafloor after death was the principal mechanism by which the thick chalk deposits characteristic of late Cretaceous marine sediments were formed. The White Cliffs of Dover, the chalk plateaus of northern France, and equivalent deposits across Europe and North America are the accumulated remains of these organisms, laid down at rates of approximately 1 centimeter per 1,000 years across the shallow seas of the Maastrichtian. The productivity of the late Cretaceous ocean was ultimately grounded in the photosynthetic activity of phytoplankton in the upper sunlit layer, the euphotic zone extending from the surface to a depth of approximately 100 to 200 meters, depending on water clarity. This thin surface layer, representing a tiny fraction of the total ocean volume, captured solar energy and converted it into organic carbon that supported the entire food web below. The efficiency of energy transfer from phytoplankton through zooplankton to fish to apex predators meant that the large, metabolically demanding animals at the top of the food web, the mosasaurs, the large sharks, the plesiosaurs, were ultimately dependent on the continued productivity of organisms invisible to the naked eye, distributed across the surface of the ocean in concentrations of millions of cells per liter of seawater. This dependency, the structural reliance of the entire marine food web on the continued function of microscopic primary producers in the surface ocean, was the fundamental vulnerability of the late Cretaceous marine ecosystem. It was not a weakness in any ordinary sense. It was simply the architecture of the system, the same architecture that has characterized marine food webs across hundreds of millions of years of ocean history. Under stable conditions, the productivity of the surface ocean was effectively inexhaustible on ecological timescales, continuously renewed by the circulation of nutrients from depth and the availability of solar energy. The mosasaurs and ammonites and large predatory fish that occupied the upper levels of the food web had no evolutionary experience of conditions under which that productivity might be interrupted on a global scale, and for a duration exceeding any seasonal or interannual variability they had encountered across their evolutionary history. The ocean they inhabited was a system optimized by selection for the conditions that had prevailed continuously across millions of years, and those conditions were about to change faster than any biological system could adapt. The atmosphere that surrounded Earth in the final hours of the Cretaceous was, in its basic chemical composition, not fundamentally different from the atmosphere of today. It was nitrogen-dominated, oxygen-rich, and contained carbon dioxide at concentrations elevated above modern pre-industrial levels, but within the range that complex multicellular life had inhabited continuously across hundreds of millions of years. Solar energy reached the surface at intensities sufficient to drive the photosynthetic productivity of terrestrial and marine ecosystems across the full extent of the planet. The atmospheric system was dynamic, as it has always been, but it was operating within parameters that the biosphere had shaped and adapted to across geological timescales. Within hours of the Chicxulub impact, and compounded at whatever temporal separation applied by the Nadir impact, that atmosphere began a transformation whose speed and magnitude had no precedent within the evolutionary experience of any organism alive at the time. The first atmospheric effect was thermal. The re-entry of ejecta, the material lofted into the upper atmosphere and beyond by the energy of the impact, produced a pulse of infrared radiation at the surface of sufficient intensity to ignite vegetation across continental areas with line-of-sight exposure to the descending particle curtain. Models of ejecta re-entry dynamics indicate that the thermal pulse associated with the return of ballistic ejecta from the Chicxulub impact may have lasted for tens of minutes to several hours, delivering radiant energy to the surface at rates comparable to or exceeding those of a broiler oven across affected regions. The ignition of wildfires under these conditions was not a localized phenomenon. Charcoal deposits, the geological signature of large-scale burning, are found in latest Cretaceous sedimentary layers across multiple continents, consistent with widespread fire activity in the immediate aftermath of the impact. The combustion of vegetation and organic material added carbon dioxide, carbon monoxide, and soot to the atmosphere. Soot, fine carbonaceous particles produced by incomplete combustion, is particularly effective at absorbing incoming solar radiation when suspended in the upper atmosphere. The quantity of soot injected into the stratosphere by impact-triggered wildfires, combined with the fine silicate dust lofted directly by the impact itself, represents the primary mechanism by which the impact events produced a sustained reduction in surface solar irradiance, the phenomenon commonly referred to as impact winter, though the analogy to seasonal winter substantially understates both the duration and the severity of the condition. The sulfur released by the Chicxulub impact contributed an additional and chemically distinct aerosol burden to the stratosphere. The target rock at Chicxulub included thick sequences of anhydrite and gypsum, sulfate-rich evaporite minerals whose vaporization at impact temperatures released sulfur dioxide and sulfur trioxide directly into the upper atmosphere. Once in the stratosphere, these sulfur gases reacted with water vapor and hydroxyl radicals to form sulfate aerosol particles, tiny droplets of sulfuric acid that are highly effective at scattering incoming solar radiation back to space. Estimates of the sulfur released by the Chicxulub impact range from tens of billions to hundreds of billions of tons, sufficient to produce a stratospheric aerosol layer orders of magnitude denser than that produced by any volcanic eruption in recorded human history. The 1991 eruption of Mount Pinatubo, which injected approximately 20 million tons of sulfur dioxide into the stratosphere and produced a measurable global temperature reduction of approximately 0.5 degrees Celsius over the following 2 years, provides a comparative reference point that illustrates both the mechanism and the enormous difference in scale. The combined optical depth of the stratospheric aerosol and soot layers following the Chicxulub impact, with the Nadir impact potentially adding to that burden, reduced the solar energy reaching the surface to a fraction of its normal value. Current models estimate that photosynthetically active radiation at the surface may have fallen below the compensation point, the minimum light intensity required for net photosynthesis, across much of the planet's surface within weeks of the impact. Below the compensation point, plants consume more energy through respiration than they gain through photosynthesis and cannot sustain growth. Sustained suppression of solar radiation below this threshold effectively halts the input of new energy into terrestrial ecosystems at its biological source. The forests, grasslands, and coastal vegetation of the late Cretaceous were not adapted to darkness. No complex terrestrial ecosystem had ever been required to function without sunlight across a period of months to years. The duration of significant light reduction is estimated based on aerosol and soot residence time models at months to years for the most severe phase, with partial recovery of surface irradiance occurring over a period of years to decades as particles settled from the stratosphere. During this interval, surface temperatures fell across continental interiors. Models suggest cooling of 10 to 20 degrees Celsius or more in continental regions during the peak impact winter phase, with the magnitude and duration of cooling varying by latitude and proximity to the moderating influence of ocean thermal mass. Coastal and oceanic regions experienced less severe temperature reduction due to the high heat capacity of the ocean, but the reduction in solar irradiance affected marine photosynthesis regardless of temperature, since phytoplankton productivity is driven by light availability rather than temperature alone within the range of conditions prevailing in the late Cretaceous ocean. The chemical consequences of the impact for atmospheric composition extended beyond sulfate aerosols and soot. The enormous energy of the Chicxulub impact heated atmospheric nitrogen and oxygen in the fireball and ejector plume to temperatures at which they reacted to form nitrogen oxides, a family of reactive gases that once in the stratosphere participated in catalytic reactions, destroying ozone. The stratospheric ozone layer, which absorbs the majority of incoming ultraviolet radiation from the sun, was substantially depleted across affected regions in the aftermath of the impact. As the aerosol and soot layers eventually thinned and surface light levels began to recover, the recovering solar flux reaching the surface would have contained elevated proportions of ultraviolet radiation relative to pre-impact conditions, a condition damaging to DNA and directly harmful to the photosynthetic organisms and shallow water marine life that were simultaneously attempting to recover from the preceding period of darkness and cold. Acid rain represented a further chemical consequence of the atmospheric transformation. Sulfur dioxide from the impact reacted with atmospheric water to produce sulfuric acid, which fell as acid precipitation across continental and oceanic surfaces. Nitrogen oxides produced in the impact fireball similarly contributed to the formation of nitric acid in the atmosphere. The pH of precipitation in the months following the impact would have fallen substantially below the threshold tolerable to most freshwater organisms and to the calcium carbonate structures, shells and skeletons of marine invertebrates. The dissolution of carbonate shells by acidified seawater would have added a direct physiological stress to marine calcifying organisms already experiencing food web disruption from reduced phytoplankton productivity. Ammonites, foraminifera, calcareous nanoplankton, the organisms whose calcium carbonate structures formed the sedimentary record of the Cretaceous ocean, were simultaneously the most geologically visible and among the most physiologically vulnerable components of the marine ecosystem to this particular category of chemical assault. The atmosphere, over a period of months to years following the impacts, became the primary mechanism by which a localized energy release, geographically confined to the Gulf of Mexico and the Atlantic Ocean, was translated into a global environmental catastrophe. The physical energy of the impacts was enormous, but spatially bounded. The atmospheric consequences were not. The stratosphere circulates globally on timescales of weeks to months, and the aerosol and soot particles injected into it by the impacts were distributed across both hemispheres by stratospheric wind patterns within a period measured in weeks. An event that began at two specific points on Earth's surface became, through the medium of the atmosphere, a global perturbation affecting every terrestrial and marine ecosystem on the planet simultaneously, regardless of distance from the impact sites, regardless of the robustness of local ecosystems, and regardless of the evolutionary history of the organisms inhabiting them. The transition from a functioning biosphere to a collapsing one did not occur as a single discrete event. It unfolded as a cascade, a sequence of interconnected failures propagating through ecological systems whose internal dependencies had been built across millions of years of evolutionary history, and whose stability under ordinary conditions was a product of that history. The impacts had delivered the initial disruption. What followed was the amplification of that disruption through the structure of the biosphere itself, as the removal of foundational ecological components propagated upward and outward through food webs whose upper levels could not survive the loss of their base. The most immediate consequence of the sustained reduction in surface solar irradiance was the collapse of photosynthetic productivity across both terrestrial and marine environments. On land, the response was not instantaneous death of existing vegetation. Mature trees with substantial reserves of stored carbohydrates could persist for weeks to months in darkness. But the cessation of new growth and the progressive exhaustion of energy reserves. Herbaceous plants and ferns, which lacked the deep root systems and stored energy of woody vegetation, were affected more rapidly. The continuous production of leaves, flowers, seeds, and fruit, the biological output of the terrestrial plant community that formed the dietary foundation of the entire herbivore fauna, slowed and eventually halted as the light available for photosynthesis fell below the compensation point and remained there. The herbivores dependent on that production felt the consequences within weeks to months. Large-bodied herbivores, ceratopsians, hadrosaurs, ankylosaurs, required continuous intake of substantial quantities of plant material to sustain their metabolic demands. Triceratops, with a body mass estimated at 6,000 to 12,000 kilograms, would have required hundreds of kilograms of vegetation per day under normal conditions. The abrupt reduction in the availability of living plant material created a caloric deficit that could not be compensated by behavioral change or physiological adjustment at the timescale of the disruption. Populations of large herbivores began declining as individuals weakened, reproductive success fell to zero, and mortality rates exceeded any rate of replacement the population could sustain. The decline was not uniform. Local conditions, the availability of residual food sources, and the specific dietary requirements of different species would have produced variation in the rate of population collapse. But the trajectory across the large-bodied herbivore guild as a whole was irreversible. The collapse of herbivore populations propagated immediately into the carnivore guild that depended on them. Tyrannosaurus and other large theropod predators whose prey base consisted primarily of large herbivorous dinosaurs faced a rapidly diminishing food supply. The caloric requirements of a 10,000 kilogram apex predator are substantial, and the territorial ranges of individual animals or small groups would have needed to expand dramatically to maintain adequate food intake as prey populations declined. A behavioral adaptation that itself requires prey to exist across the expanded range in sufficient density to make hunting energetically profitable. As prey populations fell below critical thresholds, the energy expenditure of searching for and pursuing prey began to exceed the energy available from successful kills, producing a negative energy balance that accelerated the decline of predator populations in turn. The pattern of ecological collapse on land was therefore not a uniform simultaneous extinction, but a structured unraveling, proceeding from the base of the food web upward, with the timing of population collapse varying by trophic level, body size, dietary specificity, and the specific environmental conditions of different regions. Species with generalized diets, small body sizes, and low absolute caloric requirements were better positioned to persist through the period of resource scarcity than large-bodied dietary specialists. This differential vulnerability was not a product of any special adaptation to catastrophic conditions. It was simply a consequence of the relationship between body size, metabolic demand, and the minimum resource availability needed to sustain a viable population. The organisms that survived were not those best adapted to the post-impact world. They were those whose pre-existing characteristics happened to fall within the range compatible with survival under conditions that had never previously existed. The terrestrial plant community itself did not disappear entirely. Spores and seeds, the dormant propagules of ferns, gymnosperms, and angiosperms, persisted in the soil through the period of darkness and cold, preserving the genetic information needed to reconstitute plant communities once conditions permitted. The fossil record of the Cretaceous-Paleogene boundary preserves a characteristic pattern in its pollen and spore record, an abrupt decline in angiosperm pollen, representing the collapse of the flowering plant community, followed by a brief but pronounced spike in fern spores, representing the rapid colonization of disturbed, vegetation-stripped landscapes by ferns as light levels began to recover. This fern spike, observed in boundary sections across the world, records the ecological succession of a devastated terrestrial plant community, beginning a slow process of reconstitution from dormant propagules, a process that restored ground cover within years to decades, but required much longer timescales to rebuild the structural complexity of forest ecosystems. In the marine environment, the collapse of photosynthetic productivity in the surface ocean drove a parallel cascade through marine food webs. Calcareous nanoplankton, the primary producers responsible for the majority of open ocean primary productivity in the late Cretaceous, experienced catastrophic population crashes in the immediate aftermath of the impact, as light levels in the euphotic zone fell below those required to sustain net photosynthesis. The geochemical record of this collapse is preserved in the sedimentary layers immediately above the Cretaceous-Paleogene boundary, where the abundance of calcareous nanofossils drops precipitously and the size and diversity of surviving forms are dramatically reduced relative to latest Cretaceous assemblages. The recovery of nanoplankton communities in the earliest Paleogene was slow and proceeded through a succession of opportunistic, small-bodied taxa before more diverse assemblages gradually re-established over hundreds of thousands of years. The zooplankton communities that depended on nanoplankton productivity, including foraminifera, copepods, and the larvae of marine invertebrates, experienced corresponding declines as their food source diminished. The foraminifera, single-celled organisms whose calcite shells accumulate on the seafloor in vast quantities, and whose evolutionary record provides one of the most detailed continuous archives of ocean conditions available to paleoceanographers, show one of the most dramatic turnover events in their entire evolutionary history at the Cretaceous-Paleogene boundary. The diverse, morphologically complex planktonic foraminifera of the Maastrichtian forms with elaborate ornamentation, multiple chambers, and specialized adaptations to different depth habitats within the water column were almost entirely eliminated. The earliest Paleogene foraminifera fauna was dominated by small, simple, morphologically primitive forms that had survived at low abundance through the Cretaceous and rapidly expanded into the vacated ecological space as conditions slowly improved. The collapse of zooplankton communities removed the food source for the small fish and planktivorous marine animals that formed the intermediate levels of the marine food web, and those losses, in turn, propagated upward to the large predatory fish, marine reptiles, and other apex consumers whose populations were already under stress from the direct effects of the impact. Mosasaurs, which required continuous intake of large quantities of fish and cephalopods to sustain their body masses, faced a food web that was disintegrating beneath them. The ammonites, simultaneously stressed by ocean acidification, reduced primary productivity, and the collapse of the zooplankton communities they preyed upon, declined across all ocean basins. The combination of multiple simultaneous stressors, light reduction, temperature change, ocean acidification, and food web collapse produced a rate of extinction in the marine realm that exceeded anything the ocean had experienced since the end Permian extinction approximately 186 million years earlier. On the seafloor, benthic communities experienced a different pattern of disruption. Organisms dependent on the rain of organic material from the surface ocean, the biological pump that continuously transferred carbon and nutrients from the productive surface layer to the deep, faced starvation as surface productivity collapsed and the flux of sinking organic particles diminished to a fraction of its pre-impact rate. Deep-sea foraminifera, which had been relatively buffered from surface events during previous extinction crises due to the stability of the deep ocean environment, experienced significant extinction at the Cretaceous-Paleogene boundary, a reflection of the severity and depth of the disruption to surface productivity that formed their ultimate energy source. The world that emerged in the first years and decades after the impact was a biologically impoverished version of the world that had preceded it. Ecosystems that had been structured by millions of years of evolutionary interaction, predator and prey, plant and pollinator, parasite and host, had been disrupted at their foundations. The survivors, whatever their taxonomic identity and ecological role, inhabited a world in which the competitive and predatory pressures that had shaped their evolutionary history were temporarily relaxed. The resources that had been monopolized by dominant species were suddenly available, and the ecological space that had been occupied continuously since the Triassic by the non-avian dinosaurs and the marine reptiles was empty. The conditions for the next phase of life on Earth were being established in the ruins of the one that had just ended. Not everything died. This is the fact that the fossil record preserves with as much fidelity as the evidence of destruction, that through one of the most severe disruptions to the global biosphere in the history of complex animal life, a subset of species persisted, reproduced, and ultimately gave rise to the ecosystems that would come to define the subsequent era. The survival of these lineages was not random in the statistical sense of being entirely unpredictable. It was structured by biological and ecological characteristics that, in the specific conditions produced by the impact winter and its aftermath, conferred meaningful advantages on their bearers. Advantages that had not been selected for in anticipation of catastrophe, but that happened to align with the demands of survival in a world where solar energy, food resources, and environmental stability had all been simultaneously and drastically reduced. Body size was among the most consequential of these characteristics. The relationship between body mass and metabolic demand is not linear. Larger animals require disproportionately more energy per unit time to maintain basic physiological function, which meant that the collapse of primary productivity imposed its most severe caloric constraints on the largest-bodied animals first. The survivors among terrestrial vertebrates were overwhelmingly small. The mammals that persisted through the Cretaceous-Paleogene boundary were, with few exceptions, animals weighing less than a kilogram, creatures whose absolute daily caloric requirements were low enough that they could be met from food sources that remained available even as the broader food web contracted. Insects, seeds, fungal material, decaying organic matter, and the small invertebrates associated with leaf litter and soil environments constituted a resource base that, while reduced from its pre-impact abundance, was not eliminated in the way that living vegetation and large vertebrate prey were. The mammals that had spent the Cretaceous occupying these low-level niches, generalist feeders in the understory and leaf litter, were, by accident of their ecological position, precisely the animals whose diet remained viable through the most severe phase of the environmental disruption. Dormancy and torpor provided an additional survival mechanism for some lineages. The ability to reduce metabolic rate dramatically during periods of food scarcity, entering a physiological state in which energy expenditure falls to a small fraction of the active rate, extended the interval over which an animal's stored energy reserves could sustain survival. Evidence from the modern distributions and physiological capabilities of mammals suggests that torpor was a feature of some Cretaceous mammal lineages, and the capacity to enter extended periods of dormancy would have substantially increased the probability of surviving a prolonged period of reduced food availability. Whether specific surviving lineages employed this strategy cannot be determined from the fossil record with certainty, but the physiological evidence from their descendants makes it a reasonable inference. The survival of birds, avian dinosaurs, through the Cretaceous-Paleogene extinction is one of the most significant evolutionary outcomes of the event, and the characteristics that permitted it illuminate the same principles visible in mammalian survival. Of the multiple lineages of birds present in the latest Cretaceous, only a subset survived into the Paleogene. The Hesperornithines, large flightless diving birds, did not survive. The Enantiornithines, a diverse and globally distributed group of perching and flying birds that had been among the most successful avian lineages of the Cretaceous, were eliminated entirely. The lineage that survived, and from which all modern birds descend, was characterized by small body size, generalized dietary capabilities, and, crucially, the absence of dependence on forest ecosystems for nesting and food. Current evidence suggests that the surviving bird lineages were ground-dwelling or associated with open, non-forested environments and had dietary repertoires that included seeds, a food source that, encased in resistant seed coats and capable of persisting in soil for extended periods, remained available long after living vegetation had died back. The role of freshwater ecosystems as refugia during the extinction event is supported by a pattern visible across multiple vertebrate groups. Freshwater environments, rivers, lakes, floodplains, and their associated wetlands buffered their inhabitants against some of the most severe consequences of the impact winter through mechanisms related to the thermal inertia of water and the availability of food sources independent of terrestrial photosynthesis. Freshwater food webs are substantially supported by the input of dead organic material, leaf litter, woody debris, terrestrial invertebrates from surrounding terrestrial environments. As the collapse of terrestrial plant communities produced large quantities of dead organic material, freshwater systems initially received an enhanced input of this detrital resource, temporarily sustaining the productivity of decomposer-based food webs, even as photosynthesis-based food webs contracted. Turtles, crocodilians, freshwater fish, and freshwater invertebrates all show substantially higher survival rates across the Cretaceous-Paleogene boundary than their terrestrial or marine counterparts, a pattern consistent with the detrital subsidy hypothesis and with the general thermal and chemical buffering provided by freshwater environments. Crocodilians deserve particular attention as survivors. By the latest Cretaceous, crocodilians had diversified into a wide range of ecological forms, including terrestrial and semi-terrestrial species, fully aquatic ocean-going forms, and the more generalized semi-aquatic ambush predators, whose basic body plan persists in modern crocodiles and alligators. It was the semi-aquatic generalists that survived the extinction. Their survival can be attributed to a combination of characteristics: ectothermy, which reduced their absolute caloric requirements relative to similarly sized endothermic animals; the capacity to survive extended periods without food. Modern crocodilians can survive for over a year without feeding under appropriate temperature conditions; and dietary generalism that allowed them to exploit whatever animal protein was available in freshwater environments. These were not adaptations to catastrophe. They were the ordinary biological characteristics of a successful predator lineage that happened to align with survival requirements in a world where food was scarce and environmental conditions were unstable. The insects that survived the extinction provided a critical foundation for the recovery of terrestrial food webs. insect diversity was reduced across the boundary, and specific groups associated with flowering plants, particularly those involved in pollination relationships, experienced significant losses as their host plants declined. But the basic insect fauna, particularly the detritivorous and decomposer groups that processed dead organic material, persisted through the impact winter and formed an early and essential component of the post-impact terrestrial ecosystem. The survival of insects ensured that the small insectivorous mammals and birds that depended on them had a continuing food source during the recovery phase, and that the decomposer pathways essential for nutrient cycling in recovering terrestrial ecosystems remained functional. The evolutionary bottleneck imposed by the extinction had consequences that extended far beyond the immediate survival or death of individual species. Populations that survived the boundary were, in most cases, drastically reduced in size. The genetic diversity of surviving lineages was compressed by the elimination of a large proportion of individuals, producing founder effects and genetic drift that would shape the evolutionary trajectories of descendant lineages across the subsequent millions of years. The mammals that survived into the Paleogene did so as small, scattered populations whose genetic diversity had been substantially reduced relative to their Cretaceous predecessors. The rapid diversification of mammals in the early Paleogene, the explosive radiation of new body plans, ecological roles, and dietary strategies that would eventually produce the full diversity of modern mammalian orders, proceeded from this narrow genetic foundation, driven by the relaxation of competitive and predatory pressures, and the availability of vast quantities of unoccupied ecological space. The world that the survivors inherited was not immediately hospitable. The early Paleogene environment was physically and chemically disturbed, biologically impoverished, and climatically unstable as the stratospheric aerosol burden slowly dissipated and the carbon dioxide released by the impacts and wildfires began to drive a gradual warming that would eventually more than compensate for the preceding cold. The recovery of terrestrial ecosystems from the impact winter to something resembling pre-impact complexity required, by most estimates derived from the fossil record, on the order of hundreds of thousands to millions of years, timescales that dwarf any human frame of reference, but that are, in geological terms, remarkably rapid for the reconstruction of complex biological systems from a state of severe disruption. The creatures that endured did not survive into a waiting world. They survived into a vacancy, and what filled that vacancy over the subsequent millions of years was shaped entirely by the biological characteristics they carried with them across the boundary. The reconstruction of events that occurred 66 million years ago rests on physical evidence, material preserved in rock, sediment, and mineral structure across the intervening geological time, interpreted through a set of analytical techniques whose precision and resolving power have expanded substantially over the past several decades. The story of the Nadir Crater and its relationship to the end Cretaceous extinction is, at its foundation, a story about detection, about the methods by which scientists extract information from geological materials, the instruments that make that extraction possible, and the inferential framework through which physical measurements are translated into reconstructions of ancient events. The initial identification of the Nadir Crater in 2022 was made possible by seismic reflection profiling, a technique that uses controlled acoustic energy sources to generate sound waves that propagate downward through the seafloor and reflect off boundaries between rock layers of differing acoustic impedance. The reflected signals are recorded by hydrophone arrays towed behind survey vessels, and the travel times and amplitudes of the returning signals are processed into images of subsurface structure that can resolve geological features at scales of meters to tens of meters across depths of kilometers below the seafloor. The two-dimensional seismic dataset that first revealed the Nadir structure was collected during surveys conducted for petroleum exploration purposes, the Guinea Plateau and adjacent Atlantic margin being a region of interest for hydrocarbon prospecting, and the anomalous circular structure buried beneath the sediment column was identified by researchers analyzing that existing dataset. Rather than through a purpose-designed scientific survey, the 2024 confirmation of the crater's impact origin relied on three-dimensional seismic data, a more recently developed and considerably more information-rich variant of the same basic technique, in which closely spaced parallel survey lines are combined to produce a volumetric image of subsurface structure rather than a series of individual cross-sections. Three-dimensional seismic imaging allowed researchers to map the full spatial geometry of the Nadir structure at a resolution sufficient to identify the diagnostic morphological features of a complex impact crater, the near-circular faulted rim at 9.2 kilometers diameter, the central uplift rising 350 meters from the crater floor, the concentric system of normal faults extending outward to approximately 23 kilometers, and the spiral geometry of thrust faults within the crater floor. These features, taken together, constitute a morphological signature that cannot be produced by any known geological process other than hypervelocity impact, and their identification in the three-dimensional dataset provided the definitive basis for confirming the structure's impact origin. The physical process that the seismic data records is the contrast in acoustic properties between different rock and sediment types. A layer of impact melt or suvite, the mixture of fragmented rock and glass produced by the impact, has different density and elastic properties than the surrounding undeformed sediment, and this contrast produces a reflective boundary visible in the seismic record. The deformation structures surrounding the crater, the faults, the folded and disrupted sediment layers, the zones of chaotic reflection character that indicate physically disturbed material, are similarly visible as anomalous patterns within the otherwise regular layered stratigraphy of the Guinea Plateau sediment column. The 66 million years of sediment that have accumulated above the crater since its formation have, paradoxically, aided its preservation and detection by protecting the impact structure from erosion, while simultaneously providing a context of undisturbed stratigraphy against which the disrupted crater morphology is clearly visible. The stratigraphic position of the Nadir crater within the seismic data, its relationship to the surrounding sediment layers above and below, is what constrains its age to the Cretaceous-Paleogene boundary interval. The sediment layers that overlie the crater were deposited after its formation and belong to the Paleogene. They are the ongoing accumulation of pelagic and hemipelagic sediment that has been settling onto the Atlantic floor since the impact. The layers that the crater disrupted and deformed belong to the Cretaceous. The stratigraphic position of the impact horizon within the sediment column therefore places the crater's formation at or very near the boundary between these two geological periods, approximately 66 million years ago. But stratigraphic position provides only relative age. The determination that the crater formed at a particular point in the sedimentary sequence, rather than the absolute numerical age needed to determine whether the Nadir impact was simultaneous with, earlier than, or later than the Chicxulub event. Obtaining an absolute age for the Nadir crater requires physical samples from the crater itself. The standard geochronological techniques applicable to impact structures, including uranium-lead dating of zircon crystals that were melted and recrystallized at impact temperatures, and argon-argon dating of impact melt glasses require gram-scale quantities of appropriately processed material extracted directly from the crater's impact melt sheet or suvite layer. Recovering those samples from a structure buried beneath 300 meters of seafloor sediment in 900 meters of water requires scientific ocean drilling, the deployment of specialized drilling vessels equipped to core through deep water sediment columns and recover intact cylindrical samples of rock from specified target depths. A drilling proposal targeting the Nadir Crater has been developed by the research team, with planned operations that would recover cores from the crater's suvite layer and the sediment immediately above and below the impact horizon. These cores, once recovered, would be subjected to a range of analytical procedures beyond geochronological dating, geochemical analysis of the impact melt and suovite for platinum group element concentrations, iridium, osmium, platinum, and related elements that are enriched in extraterrestrial material relative to terrestrial crustal abundances, would provide evidence of the impactor's composition and potentially allow comparison with the geochemical signature of the Chicxulub impactor. If the two impactors shared a common parent body, their platinum group element ratios might be expected to show corresponding similarities, though the analytical precision required to detect such similarities against the background variability of meteoritic compositions would be considerable. Microscopic examination of mineral grains from the crater's impact horizon would reveal the presence and character of shock metamorphic features, the planar deformation features in quartz, the high-pressure mineral polymorphs such as coesite and stishovite, and the partially or fully isotropic glass produced by extreme shock pressures, whose characteristics record the peak pressures experienced by the target rock during the impact and provide independent confirmation of the hypervelocity impact origin, already established by the seismic data. The size distribution and spatial pattern of ejecta particles within the suvite layer could be used to constrain the dynamics of crater formation, and the chemical composition of impact glass could be compared with the composition of the underlying target rock to reconstruct the mixing and fractionation processes that occurred during the impact. The sediment cores recovered from above the crater would provide a record of the environmental aftermath of the impact at a location proximal to the impact site, a record potentially containing signatures of the tsunami deposit, the ejecta fallout layer, the acid rain event, and the subsequent recovery of marine microfossil communities in the earliest Paleogene. The microfossil record immediately above the impact horizon, the foraminifera, calcareous nanoplankton, and other organisms whose remains accumulate continuously in marine sediment, would record the local biological response to the Nadir impact with a temporal resolution potentially finer than that available from more distal sites, providing evidence for the duration and severity of the local environmental disruption and its relationship to the global pattern of extinction and recovery documented elsewhere in the Cretaceous-Paleogene boundary record. The scientific detective work surrounding the Nadir Crater is therefore still actively in progress. The confirmation of its impact origin in 2024 resolved the foundational question of what the structure is. The questions that remain: its precise age, its relationship to Chicxulub, the magnitude of its environmental consequences, and whether it was part of a larger cluster of impact events, are questions that only physical samples can answer. The instruments and analytical techniques needed to address those questions exist. The drilling infrastructure capable of recovering the samples exists. What remains is the execution of the scientific program that will bring the physical evidence from beneath 1,200 meters of water and rock to the surface, where it can be examined directly for the first time since it was formed. In the last moments of the Cretaceous, 66 million years ago, The question of whether the Nadir and Chicxulub impactors shared a common origin is, at its foundation, a question about the structure and behavior of the solar system's small body population in the geological past, a domain where direct observational evidence is sparse and where inference from physical models, astronomical surveys, and the terrestrial impact record must substitute for observation. The solar system contains an enormous number of small bodies, asteroids, comets, and their fragments, distributed across a range of orbital populations whose dynamics are governed by gravitational interactions with the planets, particularly Jupiter, and by non-gravitational forces, including the Yarkovsky effect, a subtle but cumulative thermal force produced by the anisotropic re-radiation of absorbed solar energy from a rotating body. Over timescales of millions to tens of millions of years, these forces can drive significant evolution in the orbital parameters of individual objects, delivering bodies from the main asteroid belt into the inner solar system where they become near-Earth objects and, eventually, potential impactors. Within this population, two categories of multi-body configuration are particularly relevant to the question of the Nadir and Chicxulub impactors. The first is the binary asteroid system, a gravitationally bound pair of objects orbiting a common center of mass, which, as noted in astronomical surveys of the near-Earth population, characterizes approximately 15% of asteroids larger than 200 meters in diameter. Binary systems form through several mechanisms, including the Yorp effect, a rotational acceleration produced by thermal re-radiation that can spin a loosely consolidated asteroid to the point where material is shed from its equatorial region and enters orbit around the primary body, and through tidal disruption during close planetary encounters. A binary system encountering Earth's gravitational field would experience differential perturbations on its two components as it approached, potentially disrupting the mutual orbit and delivering both objects to Earth impact trajectories within a period of hours to days. The second relevant configuration is the asteroid family, a population of fragments produced by the catastrophic disruption of a larger parent body through collision with another asteroid in the main belt. Asteroid families are well documented in the modern asteroid population. The Baptistina family, produced by a collision estimated to have occurred approximately 160 million years ago, has been proposed as a potential source of the Chicxulub impactor, though the precise timing and dynamics of this connection remain debated. A family-forming collision in the main belt produces a dispersed cloud of fragments on broadly similar but not identical orbital trajectories. Over millions of years, the differential evolution of these orbits under gravitational and non-gravitational perturbations spreads the fragments across a range of orbital parameters, but a subset of fragments may retain sufficiently similar orbits to encounter Earth within a geologically brief interval, producing an elevated flux of impacts over a period of thousands to hundreds of thousands of years, rather than a single simultaneous event. The distinction between these two scenarios, binary impact versus fragmented family impact, has direct implications for the temporal relationship between the Nadir and Chicxulub events. A binary system would deliver its two components to Earth within hours to days of each other. A truly simultaneous double impact at any geological resolution. A family fragment scenario would produce impacts potentially separated by thousands to hundreds of thousands of years, an interval that is geologically simultaneous at the resolution of current dating methods, but environmentally significant in terms of whether the biosphere was absorbing one catastrophe or two sequential ones. The current age uncertainty of the Nadir Crater, approximately 1 million years, cannot discriminate between these scenarios. Only the precise isotopic dating that physical samples would enable can begin to address this question. The possibility that additional impact craters of equivalent age exist but have not yet been identified adds a further dimension to the question. The Nadir Crater was discovered within a seismic dataset collected for unrelated commercial purposes on a portion of the Atlantic floor that happened to have been surveyed at sufficient resolution to reveal a 9-kilometer structure buried beneath 300 meters of sediment. The proportion of the global ocean floor that has been surveyed at comparable or better resolution is limited. The deep ocean basins, covering approximately 65% of Earth's surface, remain, in terms of detailed subsurface geological characterization, among the least explored surfaces accessible to scientific investigation. A 9-kilometer impact crater buried beneath ocean sediment is undetectable from ocean surface observations, invisible to satellite remote sensing of the seafloor, and resolvable only through acoustic imaging at sufficient resolution. The continental impact record presents its own incompleteness. Large impact craters on land are subject to erosion, while younger sediment, tectonic deformation, and overprinting by subsequent geological processes, all of which progressively obliterate their surface expression over geological timescales. A crater formed 66 million years ago on a continental surface would, depending on the local geological history of that region, potentially retain recognizable morphology in areas of low erosion and tectonic stability, or be entirely unrecognizable in regions that have experienced significant erosion, volcanism, or deformation in the intervening time. Systematic searches for impact structures on continental surfaces using remote sensing, geophysical surveys, and targeted geological mapping have identified the approximately 200 confirmed craters currently in the global catalogue. But the completeness of that catalogue for structures of Cretaceous age is difficult to assess precisely, particularly for smaller structures in the 10-kilometer size range and below. The fossil record carries its own indirect testimony regarding the question of multiple impacts. The pattern of extinction at the Cretaceous-Paleogene boundary, its abruptness, its global extent, and the near-total elimination of certain groups, such as the non-avian dinosaurs, mosasaurs, plesiosaurs, and ammonites, is consistent with a catastrophic environmental disruption of very short duration relative to the adaptive capacity of the affected organisms. The speed of the extinction, as recorded in the highest resolution boundary sections available, is consistent with the environmental consequences of a single large impact, but does not exclude additional impacts as contributing factors. Distinguishing the environmental signature of a second impact from the background catastrophe produced by the first is analytically challenging, particularly at sites distant from the Nadir impact location, where the geochemical and physical signatures of a smaller ocean basin impact would be substantially diluted. Some boundary sections in Atlantic proximal locations show unusual complexity in their physical and geochemical stratigraphy that has not been fully explained by the Chicxulub impact alone. Anomalous sedimentary structures, unexpected variations in ejecta layer thickness, and localized geochemical signals in some Atlantic boundary sections have been noted in the literature without definitive explanation. Whether any of these features record the physical signature of the Nadir impact, its tsunami deposit, its ejecta fallout, or its geochemical contribution to the boundary layer, cannot be determined without the precise age constraints and detailed geochemical characterization that only crater samples can provide. The possibility exists that evidence of the Nadir impact is already present in existing boundary sections, unrecognized because it was not being searched for and because the interpretive framework for the boundary, developed entirely around Chicxulub, did not include the possibility of a second impact as a variable to be accounted for. The broader context of Earth's impact history over the past 100 million years adds a statistical dimension to these questions. Impact flux models derived from lunar crater counts and near-Earth object surveys indicate that impacts in the Nadir size range, objects 400 to 500 meters in diameter, occur at average intervals of approximately 100,000 years or more. The occurrence of such an impact within the same geological instant as a Chicxulub-scale event, under a random impact flux model, represents a probability low enough to constitute meaningful evidence for a non-random explanation. That non-random explanation need not involve a direct physical connection between the two impactors. It could, in principle, reflect an episodic enhancement of impact flux during the late Cretaceous, driven by a dynamical event in the main asteroid belt, or by the passage of the solar system through a region of elevated small body density. Such episodic enhancements have been proposed in the scientific literature in connection with proposed periodicity in the terrestrial impact record, though the evidence for true periodicity in impact flux remains contested. What the current state of evidence establishes, without ambiguity, is that Earth was struck by at least 2 significant asteroid impacts within the same geological boundary interval that defines one of the 5 largest mass extinctions in the history of complex animal life. The mechanisms connecting those events, physical, dynamical, and environmental, remain incompletely understood. The questions they raise about the completeness of the known impact record, the dynamics of the late Cretaceous near-Earth object population, and the cumulative environmental consequences of multiple near-simultaneous impacts are well defined, scientifically tractable, and answerable in principle through the combination of ocean drilling, geochemical analysis, and continued astronomical and geophysical survey that the current state of the science makes possible. The end of the Cretaceous period is recorded in the geological column as a thin layer, in most boundary sections, a few centimeters of iridium-enriched clay separating 2 fundamentally different biological worlds. Below that layer, the fossil assemblages of the Maastrichtian, diverse non-avian dinosaurs, mosasaurs, plesiosaurs, ammonites, complex planktonic foraminifera, and the full ecological architecture of a biosphere that had been developing continuously since the Triassic. Above it, an impoverished early Paleogene fauna, small, generalized, taxonomically reduced, beginning the long process of rebuilding ecological complexity from a drastically contracted biological foundation. The boundary layer itself, deposited over a period estimated at years to decades, contains the physical record of the transition. Iridium from the vaporized impactors, shocked mineral grains, spherules of impact-generated glass, and in some sections, the charcoal signature of widespread burning. It is one of the most studied stratigraphic horizons in the geological record, sampled and analyzed in boundary sections on every continent and in cores from ocean basins worldwide. And it records, in the language of chemistry and mineralogy, the moment when the trajectory of life on Earth was permanently altered. The scale of biological loss at the Cretaceous-Paleogene boundary is most precisely expressed in terms of species-level extinction rates. But the deeper significance of the event lies not in the number of species eliminated, but in the ecological architecture that was dismantled. The non-avian dinosaurs had occupied the large-bodied terrestrial vertebrate niches, herbivore, omnivore, apex predator, continuously for approximately 165 million years, since their rise to ecological dominance in the late Triassic, following the end Triassic extinction. Their elimination did not merely remove a set of species from the roster of life, it vacated an entire ecological tier of the terrestrial biosphere, the large-bodied vertebrate guild that had been occupied without interruption for longer than the current age of flowering plants. The magnitude of that vacancy and the speed with which it was created had no precedent in the evolutionary history of terrestrial vertebrates. In the marine realm, the simultaneous loss of mosasaurs, plesiosaurs, and ammonites removed the dominant large-bodied predators and the most numerically abundant large invertebrates from ocean ecosystems that had been structured around their presence for tens of millions of years. The near-total collapse of planktonic foraminifera diversity and the catastrophic reduction in calcareous nanoplankton productivity disrupted the biological pump, the process by which surface ocean productivity transfers carbon to the deep sea at a global scale, altering the chemistry of the ocean over timescales of thousands to tens of thousands of years as the system adjusted to the loss of its primary biological drivers. The recovery of marine ecosystems from this disruption was measured in millions of years, not thousands, and the ocean that eventually emerged from the recovery was ecologically and taxonomically a fundamentally different system from the one that had entered the boundary interval. The combined environmental consequences of the Chicxulub and Nadir impacts, operating through the atmosphere, the ocean, and the terrestrial biosphere simultaneously, produced a crisis of a character distinct from the other major extinction events in Earth's history. The end Permian extinction, approximately 252 million years ago and the most severe in the history of complex animal life, was driven primarily by the prolonged volcanic activity of the Siberian traps, operating over timescales of hundreds of thousands of years and producing environmental deterioration that, while ultimately catastrophic, allowed some degree of adaptive response across generations. The end Cretaceous crisis was different in kind as well as magnitude, an instantaneous physical disruption delivering its primary environmental consequences within hours to years, against which no behavioral or physiological adaptation was possible within the time frame of the event. The organisms that survived did so not because they adapted to the changing conditions, but because their pre-existing characteristics happened to fall within the narrow range compatible with survival. The rise of the survivors, the diversification of mammals, birds, and other lineages that crossed the boundary, was not a predetermined outcome of the extinction event. It was a contingent result of which lineages happened to survive, shaped by the specific environmental conditions of the impact winter and its aftermath, and by the ecological opportunities created by the removal of the dominant Cretaceous fauna. The early Paleogene mammals that began filling the vacated ecological space were not pre-adapted to the roles they would eventually occupy. They were generalists, expanding opportunistically into available niches and diversifying under the twin pressures of ecological opportunity and competitive interaction with other expanding lineages. The ungulates, primates, cetaceans, bats, and the full diversity of modern mammalian orders that characterize the Cenozoic fauna all trace their origin to this initial post-extinction radiation, to the small, generalized survivors of the boundary event expanding across an ecologically restructured world. The time required to rebuild ecological complexity from the post-extinction baseline was substantial by any measure. Estimates derived from the diversity trajectories of marine microfossils, among the most continuously and completely preserved components of the fossil record, suggest that global marine diversity took approximately 10 million years to recover to pre-extinction levels, and longer to reconstruct the ecological complexity and functional diversity of late Cretaceous marine ecosystems. Terrestrial recovery was similarly protracted. The re-establishment of closed canopy forest ecosystems, with their associated diversity of plants, insects, and vertebrates, required millions of years in most regions, with the pace of recovery varying considerably depending on latitude, local environmental conditions, and the taxonomic composition of the surviving regional fauna. The geological record of the early Paleogene therefore preserves not a single event, but a prolonged transition, the slow reconstruction of biological complexity from a contracted foundation, playing out across millions of years of evolutionary diversification and ecological assembly. The boundary layer itself marks the beginning of that transition, but the transition was not complete at any single subsequent moment. It was a continuous process of expansion, diversification, extinction, and ecological reorganization that, in a meaningful sense, has never fully ended. The modern biosphere is itself a product of that ongoing process, shaped by 66 million years of evolution from the survivors of the end Cretaceous extinction. The two impact events at the close of the Cretaceous, one in the shallow carbonate seas of the Yucatan, one in the deep Atlantic off the coast of West Africa, together represent a confluence of astronomical and geological circumstance whose probability, under any reasonable model of impact flux, was extraordinarily low. The geological record preserves the evidence of both. In the 180-kilometer scar beneath the Gulf of Mexico that has been studied intensively for 4 decades, and in the 9.2-kilometer structure beneath the Atlantic floor that was unknown until 2022 and confirmed only in 2024. Together, they define the moment when the Mesozoic ended and the Cenozoic began, when the ecological architecture of 165 million years of dinosaur-dominated terrestrial life was dismantled within a geological instant, and when the biological lineages that would eventually give rise to the modern biosphere, including the human species itself, were given the environmental conditions under which their diversification became possible. The boundary between those two worlds is preserved in a few centimeters of clay, and it is one of the most consequential boundaries in the history of life on Earth. 66 million years after the Atlantic Ocean received an asteroid traveling at 20 kilometers per second, the seafloor of the Guinea Plateau preserves the record of that event in a structure whose existence was unknown to science until 2022 and whose impact origin was unconfirmed until 2024. The Nadir Crater, 9.2 kilometers in rim diameter, buried beneath 300 to 400 meters of Paleogene sediment in approximately 900 meters of water, is not visible at the ocean surface, not detectable by satellite, and not accessible to ordinary geological observation. It exists as a pattern of acoustic reflections in seismic data, as a morphological anomaly in the subsurface stratigraphy of the Atlantic floor, and as a physical structure in the rock beneath the ocean, present continuously across the entire subsequent history of the planet, through every development in the history of life that followed its formation, without being known. The circumstances of its discovery illustrate a principle that applies broadly to the geological record of Earth's impact history: that the known catalogue of impact structures is not a complete census of impact events, but a sample biased toward the detectable. Continental craters, exposed at the surface or in shallow subsurface, are accessible to the full range of geological surveying techniques and have been systematically searched in regions where geological mapping has been conducted at appropriate resolution. Oceanic craters are accessible only through acoustic imaging of the seafloor and subsurface, a technology that has been applied comprehensively only to portions of the ocean floor, and then primarily for commercial rather than scientific purposes. The Nadir Crater was found because a seismic survey of sufficient resolution had been conducted over the Guinea Plateau for petroleum exploration. Its discovery was a consequence of the intersection of commercial survey coverage with a subsurface feature large enough to be resolved by the available data. How many comparable structures exist beneath the portions of the ocean floor that have not been surveyed at equivalent resolution cannot be determined from existing data. The preservation of the Nadir Crater across 66 million years of geological time is itself a consequence of the specific tectonic setting in which it formed. The Atlantic Ocean crust on which the crater is located formed during the early opening of the Atlantic Basin through seafloor spreading at the mid-Atlantic ridge, and has remained largely intact since the Cretaceous, neither subducted beneath a continental margin nor significantly deformed by subsequent tectonic events. The slow, continuous accumulation of pelagic and hemipelagic sediment over the crater has buried and protected the impact structure from the erosional processes that progressively obliterate impact morphology on continental surfaces exposed to weathering. The result is a crater whose structural detail, the central uplift, the concentric fault systems, the suevite fill, the spiral thrust fault geometry recording the oblique impact trajectory, is preserved with a fidelity that, combined with the three-dimensional seismic imaging capability developed in recent decades, allowed the full anatomy of a 66-million-year-old marine impact to be reconstructed in detail comparable to that available for well-studied continental craters that have been accessible to direct physical sampling for decades. The scientific program now underway around the Nadir Crater is at an early stage relative to what will eventually be possible. The 2024 confirmation of impact origin based on three-dimensional seismic data established the morphological case beyond reasonable doubt and defined the targets for the drilling program that has been proposed. When ocean drilling of the Nadir structure is accomplished, recovering cores from the suevite layer, the impact melt sheet, and the sediment immediately above and below the impact horizon, the information accessible from those samples will substantially exceed what seismic imaging alone can provide. Isotopic dating will constrain the crater's age to a precision potentially as fine as tens of thousands of years, sufficient to determine whether the Nadir impact preceded, coincided with, or followed the Chicxulub event by a geologically meaningful interval. Geochemical analysis of the impactor signature in the melt material will characterize the composition of the Nadir impactor and allow direct comparison with the Chicxulub impactor's geochemical signature. Shock metamorphic features in mineral grains will record the peak pressures of the impact and provide independent confirmation of the impact dynamics inferred from crater morphology. The sediment cores from above the impact horizon will carry a biological record of the environmental aftermath of the Nadir impact at a location proximal to the impact site, a record whose temporal resolution and geochemical detail may exceed what is available from any currently studied Cretaceous-Paleogene boundary section, given the proximity of the Guinea Plateau site to the impact-related deposits. The microfossil assemblages immediately above the boundary in those cores will record the local collapse and subsequent recovery of the marine planktonic community with a stratigraphic continuity and resolution that could provide new constraints on the duration and character of the environmental disruption attributable specifically to the Atlantic impact, as distinct from the global signal of the Chicxulub event. The Nadir Crater also carries significance for the broader scientific understanding of oceanic impact processes, a category of geological event that is, relative to continental impacts, poorly characterized from physical evidence. Of the approximately 200 confirmed impact structures in the global catalog, only 15 to 20 are confirmed marine impact events. The physical processes governing marine impacts, the interaction of the impactor with a deep water column, the dynamics of crater formation in wet target conditions, the generation and propagation of impact tsunamis, the deposition of suovite in a hydraulically active crater environment, are understood primarily through numerical modeling rather than direct geological observation, because the physical samples needed to test and constrain those models have not been available from well-preserved marine impact structures. The Nadir Crater, with its exceptional state of preservation and its complete coverage by high-resolution three-dimensional seismic data, represents the first opportunity to characterize the geological record of a deep water impact in the detail needed to validate the models and extend understanding of marine impact processes beyond what modeling alone can establish. It is a physical record of an event that contributed, in ways not yet precisely quantified, to the most consequential biological transition in the history of complex animal life: the elimination of the non-avian dinosaurs, the marine reptiles, the ammonites, and the full ecological architecture of the Mesozoic world, and the opening of the evolutionary space within which the mammalian lineages, ancestral to all modern mammals, including the human species, diversified across the subsequent 66 million years. The magnitude of that contribution, whether the Nadir impact was a secondary perturbation imposed on an extinction already driven to completion by Chicxulub, or a meaningful additional forcing that extended the duration or increased the severity of the environmental crisis, is a question that only the physical evidence from the crater can begin to answer. What the crater represents, in the most fundamental sense, is a demonstration that the geological record of Earth's most significant events is not yet fully known. A structure 9.2 kilometers across, formed at one of the most consequential moments in the history of life, remained unknown for the entirety of human history, and was confirmed as an impact crater only within the past 2 years. The tools that made its discovery and confirmation possible, high-resolution seismic imaging, three-dimensional subsurface reconstruction, the analytical framework of impact geology developed across decades of study of continental craters, are the products of a scientific enterprise whose capacity to read the geological record has expanded substantially in recent decades and continues to expand. The Nadir Crater was always there, beneath the Atlantic, preserving in its morphology and its mineralogy the record of an event that helped end one world and make possible another. It waited 66 million years to be found. The evidence it holds has been waiting just as long to be read.